Hello everyone, welcome to my channel. This channel's for educational purposes, and we do mostly theories of everything from people you've never heard of before. And today is video number 217 on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson came up with this theory in the 20th century and died back in 1990. Wrote a lot of books and articles. And we're looking at one of his books today, Nothing But Motion. Came out in 1979. We're on chapter 18, which is called Simple Compounds. This book is primarily on atomic physics, but Larson wrote books on many other subjects as well. Chemistry, including some organic chemistry, which will be coming up in this book. Also, astronomy, astrophysics. He wrote a couple books on economics. And he wrote at least chapters or articles on a lot of issues in psychology and philosophy, and religion. And some of his followers have followed up and wrote books on other subjects, crypto-archaeoastronomy and conspiracy theories, a lot of different stuff. The basic idea behind Larson's reciprocal system of theory is that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy, it is made out of motion. And motion is the relationship between space and time. Now we see that in the most basic motion that we know of, which is speed. Speed is space over time. The bicycle is moving at 20 miles per hour. 20 miles of space in 1 hour of time. Space over time equals speed. Now, when you say that motion is the relationship between space and time, you're setting up a generalized reciprocal relationship between space and time. So, when you say the bike is moving 20 miles per hour, but then you decide to double the speed, you can then say that the bike is moving 40 miles per hour. But you can also say that the bike is now moving 20 miles per half hour. You can either multiply the space or divide the time. If you want to double the speed, both of them will give you the equivalent. And that shows a reciprocal relationship. Now, there are many other different relationships, different kinds of motion other than speed. In fact, all basic scientific quantities, mechanical quantities, are relationships between space and time. They're kinds of motion. So, for example, pressure or energy, matter, acceleration, force, electric current, electric charge, magnetic flux, capacitance, electrical capacitance, electrical resistance. These are all kinds of motion, and they are all represented by a fraction with time or space as the numerator and space or time as the denominator. Now, the reason you can have so many different relationships is because space and time have their coordinate aspects, meaning that they come in multiple dimensions, three or more dimensions. So you can have, for example, matter. Matter is time to the third power over space to the third power. So time and space both have three or more dimensions. And so you have to take that into account when you come up with your fraction for motion. Coordinate space, we recognize three or more dimensions of space. But then there is also coordinate time, three or more dimensions of time. In addition to that, there are the clock aspects of space and time. Clock time, we generally recognize the clock is always getting later and later and later and later. The flow of time or the progression of time. But that motion is in no particular direction. That's what is called a scalar motion, a motion that has a magnitude but has no direction or no particular direction. So we normally recognize the flow of time. But there is also the flow of space, clock space. Space is always getting farther and farther and farther apart. And you can envision this with a balloon and a magic marker, put some dots on the balloon, blow up the balloon. You have an outward scalar motion. All of the dots are moving away from each other. If you suck in the balloon, all of the dots are moving toward each other. That is an inward scalar motion. So scalar motion does have a direction, either out or in. And you can also observe that through the Hubble telescope, that all of the distant galaxies are moving away from each other. And the further apart they are, the faster they're moving away from each other. Another analogy that you could use for clock space is to get another dimension of it is to use something like raisin bread. If you have raisin bread and you put it in the oven, all of the raisins are going to move away from each other as the bread expands. So that's adding another dimension to your balloon. Okay, then also time and space have their discrete aspect. They only come in discrete units. There is not continuity of space and time. They come in very small chunks. And those small chunks are too small for us to resolve, to see them. But there is a minimum unit of space and a minimum unit of time. And exactly 1 unit of space in 1 unit of time is the speed of light. So the speed of light in Larson's system is really the midpoint of the universe. And there is a half of the universe that's moving faster than the speed of light, and a half of the universe that's moving slower than the speed of light. He calls those the cosmic sector and the material sector, respectively. The material sector is something that we recognize in general because we live in the material sector and we make our observations and measurements from that spot. The cosmic sector also pervades our reality, but we can't really see it. So we don't know its existence, but we could. Again, because of the reciprocal relationship between space and time, everything that we know about the material sector also applies to the cosmic sector, except that you just have to reverse the roles of space and time. So, for example, in the material sector, we have coordinate time, coordinate space, and clock time, three-dimensional space, and progressing time. But in the cosmic sector, we have coordinate time and clock space, three-dimensional time, progressing through space. And those are unfamiliar concepts. And so then there are a few caveats in our ability to observe these things. and Larson deals with those also, and dealt with them earlier in this book. Now we are looking at this chapter that is on simple compounds. But, in order to get to compounds, you have to go through subatomic particles, and then you have to go through atoms, which he did earlier in this book, and then you go through cosmic atoms. Okay, so when you have an atom, you basically have two photons to start with. And these two photons, a photon is a simple harmonic motion, a wave-like motion, which is the result of two separate kinds of motion. It's a combination of motions of a translational motion and a vibrational motion 90 degrees separated from the translational motion. The resultant is your sine wave. But then some of Larson's followers objected to that, and they believe that the simple harmonic motion comes from a birotation, which is two counter-rotating systems. You combine those, and you also get a sine wave. So that controversy will be covered by us pretty soon. But for now, just know that the photon is your basic simple harmonic motion, and that's at the core of the atom. And then when you have those two photons, you need to rotate them in two different two-dimensional rotations, and that's where you get the atom from. And then there is an optional one-dimensional rotation of the whole system, and that is where the concept of valence comes from. So when you're combining atoms, at least that's the primary way that we recognize valence, is through the electric rotations. Now he's going to start talking here about magnetic valence, so the valences of those two primary and secondary two-dimensional rotations of the photon. Those will also are also relevant to the valence, which is something that is a departure from the legacy science. Now, when you have a cosmic atom, you have the same relationships, except that the roles of space and time are reversed. So in a material sector, you have the simple harmonic motion in time, while you have the rotations in space. In the cosmic sector, you have the reverse. You have the simple harmonic motions in space, and you have the rotations in time. Now, the last thing that I'll mention is just the time region and the space region. When you are in less than 1 unit of space, again, space and time are quantized. There's a minimum unit of space and a minimum unit of time. You have 1 unit, when you are dealing with a zone of action that is less than 1 unit of space, you do not have space, because there's no such thing as less than 1 unit of space. So this is completely a region of time. That's what Larson calls the time region, and that is where the atoms are the home of the atom, and the interaction of atoms to make compounds also occurs within that small space. So those are that's the realm of the time region, and the rules are reversed again in the time region as opposed to the material sector. So you have this material sector, and then you have a small subregion of the material sector that's called the time region. Then you have the cosmic sector, and you have a small region within the cosmic sector that is called the space region. The space region is where you have less than 1 unit of time. Less than 1 unit of time, you don't have time. And because there is no less than 1 unit of time, and so you have a region of only space, and that is what Larson calls the space region, and that is the realm of the cosmic atom, or what the legacy scientists call the antimatter. Okay, we're going to read a few paragraphs here from Larson, from chapter 18, Simple Compounds. Symmetry considerations favor balancing two electric displacements to arrive at the necessary space-time equilibrium, where conditions permit, but where the all-electric orientation encounters difficulties. It is possible for one of the magnetic rotations to take the positive role in the interatomic equilibrium. The magnetic valences, which apply in these magnetic electric orientations, are the most common basis of combination of division 2, where the positive valences are high and the neutral valences are excluded because the 8 minus x displacement is negative. They also make their appearance in the other three divisions where probability considerations permit. Remember, Larson divided the atoms of the periodic table into 4 different divisions, 1, 2, 3, and 4. 1 and 4 are basically where the electric valence is less than 4 or less, and 2 and 3 are where the electric valence is 4 or more. And the division 1 and 2 are part of the electropositives, and division 3 and 4 are part of the electronegatives. And that, basically is the electropositives are the left-hand side of the periodic table, and the electronegatives are the right-hand side. Okay. Each element has 2 magnetic rotations and therefore has 2 possible first-order magnetic valences. In alternate groups, the 2 rotations are equal, where no environmental influences are operative, and on this basis, the number of magnetic valences should be reduced to 1 in half of the groups. As we saw in our original consideration of the atomic rotation in Chapter 10, however, any element can rotate with an addition of positive electrical rotational displacement to the appropriate magnetic rotation, or with an addition of negative electric rotational displacement to the next higher magnetic rotation. Because of this flexibility, the limitation of the elements of alternate groups to a single magnetic valence actually applies only to the elements of division 1. Here, this restriction has no real significance, as the elements of this division make little use of the magnetic valence in any event because of the high probability of the low positive valences. To distinguish between the 2 magnetic valences, we will call the larger one the primary magnetic valence and the smaller one the secondary magnetic valence. Neither of these valences has any inherent probability advantage over the other, but the geometrical considerations previously mentioned do have a significant effect. For instance, where the magnetic valence can be either 2 or 3, a combination with a valence 3 negative element takes the form of r to the third x to this r3x2. If the magnetic valence is 2, and the form rx if the alternate valence prevails. The latter results in the more symmetrical and hence more probable structure. Conversely, if the negative element has valence 4, the R2X structure developed on the basis of a magnetic valence of 2 or 2 is more symmetrical than the R4X4 structure that results if the magnetic valence is 3, and it therefore takes precedence. Many of the theoretically possible magnetic valence compounds that are on the borderline of stability and do not make their appearance as independent units are stable when joined with some other valence combination. For example, there are 3 theoretically possible first-order valence oxides of carbon: CO2, positive electric valence; CO, primary magnetic valence; and C2O, secondary magnetic valence. The first two are common compounds. C2O is not, but there is another well-known compound, C3O2, which is obviously the combination of CO and C2O. As we will see later, this ability of the less stable combinations to participate in complex structures plays an important role in compound formation. The first order valences of the elements, the valences that have been discussed thus far, are summarized in Table 7. The great majority of the two chemical compounds of all classes are formed on the basis of these first order valences. Okay, so he has a big table here where he's showing the various groups, divisions, magnetic valences, electric valences, the elements that are involved. And this table probably deserves hours of study. I can't make heads or tails of it currently. It's not in a really good format to be able to view because the table goes on for 3 pages. Okay. And I think that is about all we have time for here. I got a little bit lost there. We were talking about, sometimes Larson goes into very simple algebra, which is enough to get you a little bit discombobbled. But we will recover and fight back and persevere. And tomorrow we will tackle the rest of the chapter, or the next section of this chapter. Because that's what it takes with Larson. You just have to kind of read it, let it wash over you, hope that you get some of it, and move on, and read it again later. All right, have a great day. Thanks for tuning in.